In this video we're going to look at geometric progressions. Well, these are just sequences where to get from one term to the next we are going to multiply by a constant each time. So for example, here's a sequence 5, 10, 20, 40, 80. This is a geometric progression because to get from one term to the next 5 to get to 10, each time we're multiplying by 2. Multiply by 2, multiply by 2, multiply by 2. Multiply by a constant each time. Here's another example, e.g. 36, 12, 4, 4 thirds, 4 ninths, and so on. Now this time you might say, oh, this is dividing by 3 each time. Well, dividing by 3 is the same as multiplying by a third. Multiplying by a third. And so indeed this is a geometric progression. Each time to get from one term to the next we multiply by a third. And it's useful in geometric progressions to think about two things, what's called the first term and the common ratio. So the first term is obvious. In our first example, the first term is 5, and we use a to stand for the first term. And the common ratio is the number we multiply by each time. So r is 2 in our first example. First term and common ratio. And in our second example, the first term, a is 36, and our common ratio, because each time we're multiplying by a third, we have r is equal to 1/3. Okay, so why do we care about these first term common ratios? Well, there are a few formulae that we often use with geometric progressions. Let's concentrate for now on our second example. Let's just look at the second example. Get rid of the first one. Okay, so here's our second example. And there's a formula called UN. And that tells us the nth term. And the formula is AR to the n minus 1. So for example, if I wanted to work out the fourth term of my formula of my sequence, I would just put my fourth term is just U4, which is AR to the 4 minus 1, which is, in this case, A is 36, R is 1/3, and 4 minus 1 is cubed. So we'd have 36 times 1/3 cubed, which happens to be 4/3, which was indeed the fourth term in our sequence. Obviously, this is useful if we're asked for, we can work out the fourth term easily, we worked out earlier, but if you wanted to work out the 50th term, or the 20th term, or whatever, then using a formula is a lot easier than just writing down the whole sequence. So let's do another example. The 8th term, U8, is AR to the 8 minus 1, which is 36 times 1/3 to the 7, which is 4/243. So that's the nth term formula. There's also something called the sum of the first n terms, so which is Sn. And the formula for that is a 1 minus r to the n over 1 minus r. And so S5, for example, tells us the sum of the first 5 terms. So in this case, S5 equals the first 5 terms as 36 plus 12 plus 4 plus 4/3 plus 4 ninths. Okay, I think that equals 53.7 returned. Again, you could use the formula, which is a lot quicker. For example, if we had to work out S100, we wouldn't want to have to manually add the first 100 terms. But just in this example, let's just check the formula for S5. S5 equals, we'll use the formula 36, 1 minus 1/3 to the power of 5, all over 1 minus 1/3. And if you work this out, it does indeed come to your same answer of, well, 484 over 9, which is the same as 53.7 return. Okay, there's one other example that comes up a lot in geometric progressions, which is called the sum to infinity. So let's just have a look at that quickly. So the sum to infinity is the sum of all of the terms in the sequence. So we use S infinite as our notation. So this would be 36 plus 12 plus 4 plus 4/3, but going on forever. So it's u1 first term plus u2 plus u3 plus u4 plus whatever, going on forever. And this thing only exists if the magnitude of r is less than 1. Because if r was 3, let's say, then our terms in the sequence would just keep getting bigger, and if we kept adding them together, then we'd end up with an infinite answer. Whereas if r is less than 1, each term of the sequence is smaller than the last, so this sum to infinite does indeed exist. And the formula for this sum infinity is very straightforward. It's just a over 1 minus r. So in this example, it's 36 over 1 minus 1/3, which is, I think, 54. So if we added all the terms in the sequence, they would never get any higher than 54. Indeed, they would approach 54 infinitely closely. And that makes sense. Remember when we did S5, we got 53.7 recurring. So even after 5 terms, we're quite close to this sum to infinity. The more terms we add, the closer we'll get to this 54 sum to infinite.